Hello, my name is John, and I'm presenting work with collaborators Vahid and Yalda titled One Class Learned Encoder-Decoder Network with Adversarial Context Masking for Novelty Detection. Anomaly detection is a process of identifying samples that differ in some respect from the training data. During the training phase, we model the distribution of training data. At test time, we check if new samples conform to this distribution. In this work, we focus on anomaly detection in computer vision, which has many commercial applications, including defect detection in manufacturing and obstacle detection in vehicle scenes. Autoencoders have been leveraged for anomaly detection by first modeling the distribution of normal data in the training phase. At test time, the reconstruction error of a sample can be used as an anomaly score. The benefit of this approach is that it does not require labels, and it's a simple framework for detecting anomalies. The drawbacks are that autoencoders often generalize to reconstruct outlier images. This is in part because they learn generic compression rather than capturing contextual information about the normal class. Context autoencoders have also been proposed for anomaly detection and mitigate some of the drawbacks faced by regular autoencoders. Context autoencoders reconstruct images that have been randomly masked. By learning to inpaint randomly masked regions, the network captures contextual information about the normal class. Some of the drawbacks are that random masking fails to consistently mask important parts of the image. Additionally, random masking cannot be effectively deployed at test time to limit the representational capacity of the network because it introduces unwanted variation in the reconstruction errors of samples. Inspired by the drawbacks faced by these previous approaches, we present OLED. OLED is an adversarial framework consisting of a reconstructor and a mask module. The reconstructor aims to reconstruct images that have been masked by the mask module. In this way, the reconstructor is minimizing a reconstruction error that the mask module is maximizing. The objective contains three components, each of which is a unique reconstruction error. At inference time, each of these components can also be used as an anomaly score. The benefits of our framework is that the reconstructor and the mask generator iteratively enhance each other's ability to model the underlying data distribution. The mask module is incentivized to mask the most important parts of the image to maximize the reconstruction error. In turn, the reconstructor has to learn to capture contextual information of the normal class in order to be able to inpaint these masked regions. Additionally, masking can be deployed at test time to limit the representational capacity of the network without introducing unwanted variations in the reconstruction error between samples. To evaluate our method, we chose three datasets that are popular in the anomaly detection literature. Two of the datasets, MNIST and CIFAR, are image datasets. The last one, UCSD, is a video dataset. On all three datasets, we're able to outperform cutting-edge methods using a variety of defined anomaly scores. Visual results show that inliers are easily reconstructed, whereas outliers are not reconstructed. This is a figure of the separability of the anomaly scores for each of the ones we defined. And we can see that for the UCSD dataset, we're able to effectively separate inliers and outliers. In conclusion, we propose a reconstruction-based approach for novelty detection in images and videos that outperforms several recent methods. Our approach is the first to use an adversarial setup to learn rich semantic representations through learned masking. And additional experiments with the mask module demonstrate that it effectively segments important pixels in the input image for both outliers and inliers. And this is an end-to-end learning process that can be extended to different modalities of data. Thank you so much for listening to our presentation.